Okay, good morning or afternoon. I'm going to go over exercise 6.3 with you. As you can see, this is just all on active filters. Dead easy. You get four active filters: bass cut, treble cut, bass boost, treble boost. Depending on where you put the capacitor, will depend on which filter it is. So here we go. So for this one, we want to work out the break frequency and the voltage gain. So the break frequency is given on the data sheet. It's 1 over 2 pi RC. What R do we actually use for this? It's the one it's next to or in parallel with. So it's the 10K. So it's 2 pi times 10. I'm just going to put K because of my spacing on here, but it is times 10 to the 3 multiplied by 4.7. I'm just going to put the micro sign there. Okay, just because of the spacing on here. Okay, plug those values into your calculator and you will get rounded 3.4. Okay, just double check that on yours. Okay, so there's my breakpoint. Just so you know, this type of filter is a treble boost. Treble boost. I'm just going to write it there. If it's in parallel, it's a treble filter. If it's in series, a bass filter. Okay. So that's that one. And then obviously the gain, dead easy. Gain is just obviously 200 divided by 10 gives me a gain of 20. You could put the minus sign there. I don't think it really matters in audio systems. I will put it there, but you don't have to have the minus sign. Okay, bass boost filter, calculate the break frequency, dead easy. 1 over, I'll write the whole thing out now. So it's 2 pi times your 300 times 10 to the 3 multiplied by 2.2 times 10 to the minus 9 because it's nano. Okay, plug those into your calculator, press your equals button, and looking at the answer there, I get 241 hertz. Okay, and it will be a low value if it's a bass type filter because you want the break frequency to be around the low frequencies, not the high frequencies. Calculate the voltage gain at the way above the break frequency. Well, because it's a bass boost, the shape of the graph, which I'm going to draw in a minute anyway, bass boosts will look something like that. So high frequencies are level, low frequencies get boosted, so it's kind of like an angle thing there. So anyway, gains above the break frequency is just going to be 300 divided by 10 gives me 30. Again, you could put the minus, you don't have to. The break frequency was 241. There's 200. There's 300. 240 is going to be just over halfway because even that's logarithmic. The gain is going to be 30. There's 10. There's 20. There's 30. There's my break point. On your ruler, on your protractor, about 45 degrees, like that. And then obviously straight across. There. Okay. A sinusoidal frequency of 5K, that's there's 5K, and amplitude 200 millivolts is applied. For the resulting output signal, what is its frequency? Well, obviously, it's going to still be 5K. We're not altering the frequency. All we're doing is altering the gain or the output voltage. So if there's 200 millivolts going in, I've got a gain of 30 there. So 2 times 3 is 6. So, 6,000 millivolts, which is 6 volts. Okay. Moving on to the next one. Should hopefully have time to do this one with you as well. Oh, you can see I've not got the best screen. 6.4. Okay, so this one is basically giving us a bass cut, voltage gain of 20, break frequency of 200. There's 100 hertz. There's 200 hertz there. Look, 200 is there. Gain of 20 is there, and it's a bass cut. There you go. Okay, passive filter would be unsuitable. Max gain equals 1 for passive filters. Does it make sense? Passive doesn't have a power supply, so you don't have op amps. So you can't actually boost them. You can only cut for passive. Maximum gain of 1. Draw the active bass cut. So I said if it's in series, it's a bass. You just saw the bass boost, so the capacitor goes into the other one for the cut. like that. Doesn't matter which way round the capacitor and the resistor go. Okay, so that's that one there. Right, I've been given a value there of 100 nano. Can I work out the ideal values? What was the gain? I think the gain was 20, wasn't it? Let's double check that. The gain was 20, yeah. Okay. Oh, gain equals 20. So we're going to have to make an assumption. I'm going to choose 1K for that one and 20K for that one. So how do I, oh, sorry, my fault. I've been given the capacitor value. Sorry, so I'm going to work out the input resistor. Sorry about that. So the break point is 1 over 2 pi RC. So we have to rearrange the equation to make R the subject. R equals 1 over 2 pi FC. Plug the numbers into your calculator. Let's go under here. So 1 over 2 pi times your breakpoint frequency, which was 200, times your capacitor value, which is 100 nano. Don't forget that's times 10 to the minus 9, people. Don't just put 100 into your calculator. Make sure you got your prefixes correct. I'll just have a look at the answer on there. We have 7.96 kilo. 7.96 kilo ohms, which is around about 8K kilo ohms. Therefore, can we make this one 20 times larger than that? So 8 times your 20, so it's going to be 160 kilo ohms if that one's 8K, because the gain was that. It's dead easy to hopefully sort these out. Hopefully that all makes sense. There is one more bit to do. Hopefully I have time to do this one. Dead easy. What are these filters? Look, if it goes down, it cuts. If it goes up, it's a boost. So I know filter A is a cut. Is it cutting the high or the low frequencies? The low frequencies, bass cut. And this one's a treble boost. Okay. What is the break frequency for this filter? There. So the break frequency, we're going to go down and read it off. Feel free to obviously pause me at any point and do it yourself. I'm sure you know how to do that anyway. 1, 2, 3, 4. 4,000. Notice it wants it in hertz. It's put hertz there. So I can't just put 4. I've got to put 4,000. Okay, so if I've got 300 millivolts going in and it's at 30K, 10, 20, 30, there's 30K. I'm getting it to about a gain of 8 at that point, I think. So the frequency won't change. We said that before a couple of minutes ago. That's still going to be 30,000. But the amplitude will be, where's the gain was 8, wasn't it? So 8, 8 times 3 is 24, so 2 point, oh, that should say volts. Mistake on the mark scheme there. There you go. You can always see they quite often make mistakes on there. Should be 2.4 volts, not hertz. Happy with that one? And then draw the circuit diagram. It's a bass. No, it's not. It's a treble cut. Treble cut looks like this in parallel with there. That goes to there. Ooh, that goes to there. A bit neater, Daniel. And that goes down to there. Okay. Right. Another treble cut one has a gain of 40. So which two values do you use? Gain of 40, obviously it's going to be those. Don't use values less than 1K. Remember to talk about input impedances. You want input impedance to be as high as possible. So they'll be the most logical values to use, okay? So resistor 1 would be 2 kilo ohms and resistor 2 will be 80 kilo ohms because it's got a gain of 40. Calculate the value of the capacitor required. What is a treble cut? So I'm going to be using the higher value, the 80K. So FB is 1 over 2 pi RC. So C equals, notice you can literally just swap them over for rearranging. It's dead easy, these equations to rearrange actually. So I hope there's no hassle with just literally swapping them over. One goes up, one goes down. Swap positions. 1 over 2 pi times your break point, which is 2K, 2,000, times your resistor value, which is 80, 1, 2, 3. So I've just written it all out in different forms. You can write it out in standard form if you prefer. What do we get on there? We get 1 nanofarad. On calculator, you have an engineering feature. So it says ENG, press that, it puts into the -9, which is nano, or to the -6, which will be micro, just because it looks nicer on the page, and when you see units in nanos or micros. I believe that is it for those filters. Okay, so have a little look over that again in your own time, and again, make sure you rate the video. I will be assessing you and seeing if you can draw all 4 filters and easily use the breakpoint equation in the near future.